For our project, we did a self-balancing robot where the purpose of the design was to make the robot balance under its own power. To physically design our robot, first we modeled what we wanted it to look like in CAD. And we modeled each piece that we were going to use in the physical model of our robot.
Each of the panels was then turned to a 2D sketch so that it could be cut out of 1/4-inch plywood on the university's laser cutter.
In the physical design of our robot, first we have our microcontroller, which is connected using I2C to the gyroscope and accelerometer module there. And on the front here as well, we have the motor drivers that are connected on the back to our microcontroller here. And the microcontroller is powered using a 5-volt regulator, which is connected to the larger battery on top, which powers the microcontroller as well as the stepper motors found down below.
The gyroscope measures the change of angle of the robot, while the accelerometer measures the acceleration of gravity. As you can see on the graph, the blue line is the gyroscope data integrated over time to give us the current angle of the robot. However, the gyroscope drifts over time because of this integration, and so the accelerometer data is needed to correct it over time. The accelerometer data, represented in red, is much too noisy to be used on its own to determine the angle of the robot. So this data, combined with the data from the gyroscope, is combined together in a complementary filter to find the angle of the robot, which is represented by green in the graph. The speed of the motors is controlled by a PID loop to control the angle of the robot to be at 0. As represented in the graph here, the proportional gain is shown in blue. The integral gain is shown in red, and the derivative gain is shown in green. These are all added up together to create the motor output in terms of speed, which is represented as orange. We found that the robot responded best when the integral portion was at a very high value, so you can see that the speed is very closely following the integral portion, which is in red.
The processed data function is called 1000 times per second on an interrupt timer. During this function, the accelerometer value in the X and Z direction is calculated, and the gyroscope value in the Y direction is calculated. Then the I2C library is called to read new values from the accelerometer and gyroscope module. Next, the angle of the robot is calculated from the accelerometer values using the inverse tangent function. That value is then put through a low-pass filter to get rid of excess noise. The value read from the gyroscope is then multiplied by a conversion factor to change it into the amount of milliradians changed since the last reading. This value is then summed up into a single value which represents the angle of the robot as calculated by the gyroscope. These two values are then combined using a complementary filter to find the angle of the robot. The derivative of the error is then calculated, and the integral of the error is added. Then the speed is calculated using the proportional, derivative, and integral of the error.
As the angle of the robot moves further away from 0, the speed of the motor is increased. If it goes the opposite direction, then the motor speed is increased in the opposite direction as well. This corrects the angle of the robot and allows it to stand on its own.